welcome to this demonstration of non-selective strategies for Meshed HVDC networks, one of the final demonstration of the Work Package 9 of Promotion project. My name is Laurent Chedeau, working in SuperGrid Institute. I am in charge of the modeling and simulation team. I will introduce this session and come back for the conclusion and the question. So, what is the agenda today? First, I will remind the context of Work Package 9. Then, we will introduce non-selective protection strategies, generalities first, and then focus on the two non-selective strategies implemented during our project: the converter breaker strategy and the full bridge converter-based strategy. After that, we will enter into the main subject with the hardware in the loop demonstration. A wide presentation of the scope of the demonstration and results, including some video sequences from the real-time simulation. Just a word about the question. We propose to let you ask your question by chat. You have some icon in the webinar panel. And we will summarize all the questions and answer them at the end of the session. Please precise the name of the section, or if you know it, the name of the speaker with your question. It will be more easy to address the good speaker. So the context. You can see here the Work Package 9 objectives. First, to integrate elements developed in other promotion work packages and implement them into the real-time simulation. Then, develop the real-time DC grid benchmark from a typical promotion reference network and specify the test plan. Then, of course, run the hardware in the loop simulation and demonstrate the different protection strategies. One important point of the project is to demonstrate interoperability. For that, we use different kinds of models, different kinds of MMC technologies, prototyped IEDs for different components, converter relay, line relay, supervisor, and above all, we implement a complete communication architecture based on the protocol IEC 61850. The last important objective of this real-time demonstration is to increase the technology readiness level of the studies. We decided to implement a supervisor to coordinate the MTDC on all stations for startup, protection, coordination, and voltage and power restoration. I said that we use some elements to develop developed in other work packages. You can see here the framework of the Work Package 9. Protection algorithms were developed and studied in a Work Package 4. DC circuit breaker specification and models in Work Package 6. Real-time models were also developed in RTDS environment and used by sheet transmission for their demonstration. In our case, using OpenRT tools, we had to develop our own models thanks to the specification. For MMC full bridge, we integrate real-time model developed by RWTH within Work Package 16. MTDC supervisors were designed and implemented following SuperGrid Institute development framework. Okay, now I let my colleague Alberto Bertinato speak about protection strategies.
Good morning. My name is Alberto Bertinato. I'm responsible of this grid protection team here in SuperGrid Institute. And in promotion, I was supporting Work Package 4, Work Package 9, WORKSPACE 12, and the short-term project Bornal. So let's have a small introduction to DC protection strategies. To deal with the problem of short-circuit faults in the HVDC grids, a protection scheme is required. The protection strategy can be divided into two stages, the fault clearing and the fault recovery. The fault clearing starts with the fault occurrence and finishes with the faulty component isolation. During this stage, the main actions are carried out by the protection component, like the breakers and the fault current limiters. Three fault clearing philosophy can be seen: the fully selective, the non-selective, and the partially selective fault clearing strategy. The second stage of the protection strategy is the fault recovery, during which the DC grid voltage and power are restored. During this stage, the main actions are strongly related to the converter controls. The DC grid protection can be regarded as a combination of three elements: system architecture, technology, and protection sequence and algorithms. The system architecture covers, for example, grid topology, size of the grid, and type of the interconnected IEC grid. Technology includes, among others, the protection component, communication means, and type of converter. Protection sequences and algorithms represent the action to be executed and their sequences during the fault handling process. The combination of those elements can result in various protection strategies. In order to assess the different protection schemes, key performance indicators have been proposed in order to take into account different characteristics in terms of performance, cost, and reliability. The proposed key performance indicators are a set of measurable values that demonstrates how effective the protection strategy is achieving key objectives. Efficiency indicators describe performances regarding fault interruption and fault recovery. They measure the impact a protection strategy can cause to the system. They are, for example, the fault interruption time, active and reactive power restoration time, voltage restoration time, and transient energy imbalance. During the protection sequence, some action may fail, and therefore the protection could not fulfill the expected performances. Failure KPIs have been defined to measure the reliability of the protection strategies. Economic key performance indicator can help to find the optimum from a techno-economic point of view. They include investment and operating costs, like cost of the breaker and cost of energy non-supplied and cost of losses. Assessment of protection strategy using those three key performance indicators have been performed within Work Package 4. A protection strategy can also be evaluated considering the technology readiness of the employed protection component. Work Package 9 had the aim to increase the TRL level of protection strategy in what concerns the hardware in the loop implementation of communication supervisor within two non-selective fault clearing strategies. Thank you for your attention. I'm going now to hand over to Pascal.
Hello, everybody. I'm Pascal Torweller. I'm a PhD candidate at SuperGrid Institute. I did my Master of Science in Electrical Power Engineering at the WP9 University of Hanover. And I'm currently in my last year of PhD at SuperGrid Institute in cooperation with University of Grenoble-Alpes. And my research interest is HVDC grid protection. I supported the promotion project mainly in the Work Package 4 and more specifically in the task T4.3. Today I will present you the converter breaker strategy. I will start with a brief introduction. I will specify the protection components and the layout. I will introduce you to the primary and the backup sequence of the strategy, and I will specify the switchgear requirements. And then I will come up with some conclusions. So there are three main types of fault clearing strategies, which are selective fault clearing, partially selective fault clearing, and non-selective fault clearing. The selective fault clearing strategy is specified by a protection zone which is defined around each busbar and each line. So once there's a fault, there's only this specific line which will be disconnected. In a partially selective fault clearing strategy, several protection zones are defined and only the dedicated zone will be tripped. In a non-selective fault clearing strategy, the entire DC grid is defined as a protection zone, and once there's a fault in the DC grid, the entire grid will be sequentially disconnected. The converter breaker strategy is part of this non-selective fault clearing philosophy and has been proposed by SuperGrid Institute during the promotion project. I will now specify the protection components and the layout on this 4-terminal promotion benchmark grid. So we can see here that the converter breaker strategy has converter breaking modules at each converter output and line breaking modules at each line end. The converter breaking module is composed of a mechanical type DC circuit breaker that we can see here in orange, in series with the residual current breaker and the pre-insertion resistor. The line breaking module uses the same type of DC circuit breaker in series with the residual current breaker, but there is no need for a pre-insertion resistor since we do not intend to reclose on a faulty cable since we consider that the fault is permanent. All switchgear devices are controlled by this DCB control block, which receives the tripping order from the relay and sends back failure information if there are any to the relay. We'll now zoom on this specific node in order to illustrate the sensor measurements and the relay communications. So each breaking module has a dedicated relay with current and voltage sensor measurements. It can further send tripping orders to the breaking module and receive failure information from the DCB control block. The converter breaking module relay may further send additional information to the MMC in order to organize the deblocking and to set up the power restoration. And each line breaking module communicates with the remote end in order to successfully identify the faulty line based on a double-ended algorithm. I now go over to the primary sequence. So the first step in the converter break strategy is to trip all the converter breaking modules in order to suppress the fault current coming from each converter. And in the second step, the faulty line is identified and the line breaking modules are tripped. Then in another step, the converter breaking modules are reclosed via pre-insertion resistors and voltage and power is subsequently restored. The whole sequence takes in between 100 and 200 milliseconds. The MMC fault right-through operation modes will be now illustrated. So in pre-fault state, all converters are controlled in droop control mode. Usually the fault event leads to a direct blocking of the MMC in a cable-based grid since there is a high current contribution. Once the converter breaking modules open, the MMC is then isolated from the DC grid and can switch to STATCO mode in order to provide some reactive power to the AC grid. When reclosing the converter breaking modules, the MMC may switch back to droop control mode and restore the voltage. Once the voltage has reached a sufficient level, the active power reference can be set up to pre-fault state, and so the primary sequence is completed. So here we see a simulation case for the primary sequence. You can see here that since there are no DC limiting inductors installed in the grid, there is a relatively high current contribution from the adjacent lines, which are now discharging in the faulty line. So we have a fault current of 30 kiloamps in the faulty line. In a second step, the converter breaking modules are tripped, and we can see in the middle graph that the current contribution from each converter is decreasing to 0. So the MMCs are then isolated, and naturally the fault current in the faulty line is also decreasing to a very low level. So now we can easily open the line breaking module. and in the next step reclose the converter breaking module in order to restore the voltage. We can see in the upper graph that the voltage is be restored in the time frame of 20 milliseconds. And once this is done, the power reference will be set automatically. And in this simulation case, the whole sequence took around 100 milliseconds. Now we come to the backup sequences. The first one is a converter breaker failure. Here we see in this 4-terminal benchmark grid that the converter breaking module near to busbar 1 is not able to open. And in the sequence, there are still all the other converter breaking modules which are able to open, and they will suppress the fault current coming from those converters. In the second step, the line breaking modules will identify the faulty line and trip and isolate the faulty line. And now there is no more current flowing through the DC grid, and the residual current breaker of the faulty device is able to open and isolate the faulty converter breaking module and the dedicated converter. And then the healthy part will be reconnected by reclosing the converter breaking modules, and voltage and power of the healthy part of the grid is restored. The time frame is exactly the same as in the primary sequence, so no difference here. We see here a simulation case with exactly the same fault location as previously in the primary sequence. We can see that after the tripping of the converter breaking modules, there's the converter breaking module 1, which is not able to open. So the MMC1 keeps feeding the fault, and the fault current is suppressed only by opening the line breaking module here at around 30 milliseconds after the fault. Then the healthy converter breaking modules reclose, and we can see that the rest of the grid is restoring the voltage and the power successfully. Second backup case is a line breaker failure. Here we can see that the LBM14 is not able to open, but since all converter breaking modules are interrupting the fault current, there's actually no current flowing through this specific relay, through this specific breaking module anymore. So the residual current breaker is now able to open and isolate the faulty line. The converter breaking modules are reclosing as in the primary sequence, and then the voltage and the power is restored. Actually here, there is no simulation case since the curves are identical to the primary sequence. We will now come to the switchgear requirements. So since the intention of the converter breaker strategy is to suppress the fault current at the output of each converter, the converter breaking module and the line breaking module for backup purpose needs to be conceived in a way that it is able to interrupt the fault current coming from one converter. In this grid with this specific converters, 20 kiloamps are sufficient for the current breaking capability of the DCBs. There's no need for fast breaker operation time, so here we consider 10 to 20 milliseconds to be sufficient. Exactly the same for the closing time. There are no DC limiting reactors installed in the entire DC grid. So this leads also to the fact that the surge arrestor energy requirement is quite low, here with 7 megajoules. And the way that it should interrupt a residual current of about several amps, which can be done by a classic vacuum interrupter or a standard SF6 chamber. So now we come to the conclusion. So we saw some advantages for the converter breaker strategy, which are mainly that there is no need for ultra-fast hybrid DC circuit breakers. This is why we decided to install mechanical type DC circuit breakers at the output of each converter and at the end of each line. There is reduced energy dissipation of each DCCB, and there's no need of DC limiting inductors. We also saw that there is no need for ultra-fast fault discrimination algorithms, since the fault is suppressed at the output of each converter, and only in the second step the faulty line is isolated by the line breaking modules. We also assume that the communication protocols as the IEC 61850 can be used for this strategy. We saw in the simulation cases that the MMC can work in STATCOM mode in order to provide some reactive power to the AC grid once the converter breaking module opened. And we also saw that the power restoration time is in between 100 to 200 milliseconds for primary and backup sequences. So there's actually no risk of transient instability when considering an AC inertia coefficient of 4 with reasonable DC power exchange. So concluding, we can say that the converter breaker strategy may ease the multi-vendor approach, is efficient in terms of costs, and shows good results in interoperability. So I will now hand over to Philipp from RWTH Aachen.
Okay, perfect. Now you should be able to hear me. So my name is Philipp Ruffing, and I'm presenting you today our work on the full bridge-based protection strategy within Work Package 9. Overall, the work, as you also can see here, we worked on this strategy also within Work Package 2 and 4, and also demonstrated it on a physical small-scale DC lab in Work Package 16. And I will introduce you a little bit later on to the specific objectives here in Work Package 9. Overall, my task during the project and especially during Work Package 4 was to develop this strategy, and overall this also was included in my PhD, which I finished this year at RWTH Aachen, and my colleague Patrick Döllmann took over here and helped SGI doing the implementation of this strategy into the real-time environment in Lyon. So from this, let's go to the next slide. Okay, that's perfect. Before we start with the full bridge-based strategy, let me quickly introduce some motivations behind it. So from an operational perspective, for sure it would be desirable to just install fast DC circuit breakers at every line end, so similar to AC transmission systems, and treat every line as individual protection zone. However, in case a DC fault occurs in the system and the voltage collapses, this will lead to very high fault currents, and the nature of a fully selective protection system is that such a fault has to be also interrupted during this high current phase. So overall, we need fast DC circuit breakers, and the circuit breakers need to absorb a lot of energy during this during this interruption process. And overall, the requirements on the DC switchgear are therefore relatively high. Moreover, to limit fault currents, we need inductive termination at every line end, so large current limiting inductors, and the breakers themselves might also require a lot of space and volume, and this especially for our promotion project where everything is focusing on offshore, weight and volume is key here. So overall, the size of the overall protection scheme within the DC system will be significant, and this might also lead to relatively high costs. And you already just heard from Patrick that from Pascal, sorry, that there are different approaches, so non-selective approaches, and the key part for this non-selective approaches is that the entire DC grid is treated as one protection zone. So in case of a fault, the entire protection zone de-energizes, and the faulted lines can be interrupted or separated during near zero current and zero voltage conditions. And a nice part here is that you also can use, instead of half bridge converters, you can use full bridge converters, and full bridge converters have the advantage to stop the energy flow from the AC to the DC grid in case of a fault, and thereby by stopping this energy flow, the network can de-energize faster, and also the converters can actively contribute to the de-energization of the network. So overall, the process can happen relatively fast, and the overall objective is to reduce the requirements on the switchgear as much as possible. So let me now guide you through the individual steps of the protection strategy and explain you a little bit what differences there might be to a fully selective strategy, for example. So regarding the detection, first, if a fault occurs, the voltage in the system collapses, and every converter within this protection zone, so which is here the entire grid, need to detect the fault as fast as possible and stop the energy flow or the energy transfer from the AC to the DC grid, so from the AC side into the DC fault. This needs to be stopped relatively quickly by suppressing the fault current. But contrary to this detection, of every converter, the corresponding converters or the corresponding switchgear also has to localize where a fault is in the system, so the faulted line has to be localized. This, however, does not need to happen as fast as, for example, the fault detection, because the fault separation occurs under an already safe environment, because the converters ensure that there is no, or that the fault current is already reduced. So overall, the localization can happen in a second step to the detection, and the requirements are lower. So here you can use also communication-based approaches, such as, for example, a differential line current protection. And this you will see later on during the presentation. After fault detection and also the localization of the faulted line, the main task of the protection strategy is to ensure near zero current and near zero voltage conditions of the respective, or at the respective fault separation units. And overall, this can achieve by just blocking the converters and naturally let the system decay to values very close to zero. However, we showed in the project that it is possible to control the full bridge converters in a way that the current flowing through this fault line. So as you can see here, for example, here we have the fault, so that we control the current flowing through this fault separation unit is reduced as much as possible and as fast as possible. And moreover, the voltage of this terminal is also reduced to values very close to zero. And therefore, we use a cascaded approach. So first, once a fault is detected, every converter just suppresses its terminal current, so the energy input from the AC to the DC system. In the second stage, the converters ensure that the DC voltage, by controlling the terminal current, that the DC voltage is close to zero. And finally, they ensure that the current flowing through the line, which shall be separated, that this is also very close to zero. And this now enables the separation of a fault using relatively or switchgear with a relatively low requirements. So overall, how could the switchgear look like? We propose here to split it into two parts: a residual DC current breaker, or in general a residual current breaker, so which might just have to interrupt several hundred amps. This under low voltages, so for example, with a counter voltage of maybe 5 to 10% of the nominal DC grid voltage ratings. And due to this, due to the control of the converters before, it can be ensured that this residual current breaker only needs to absorb a few kilojoules of energy during this interruption process. So it just needs to interrupt really like the residual current. And overall, this residual current breaker can be also adjusted to the needs of the protection strategy. So if you have to be a little bit faster, you might take a bigger residual current breaker. If there's a little bit more time, then the converters can suppress the current longer, and the amount of energy which needs to be absorbed in the residual current breaker is smaller. So after opening the residual current breaker, we can open an ultra-fast disconnector to ensure that the line now is also isolated from the healthy part of the grid. And last but not least, after fault separation and fault isolation, the voltage within the system has to be restored. And here we have to take into account that there are different grid configurations, and this might be like a symmetric monopole configuration, but also bipolar configuration. And first, maybe let's start with a bipolar configuration. You have three conductors, like a dedicated metallic return conductor, where you can have currents which more or less counteract the currents on the two healthy or the two normal poles. And therefore, it is possible to discharge and charge the poles individually. This is not possible in a symmetric monopolar configuration. So here, pole rebalancing always takes place at both poles, which might lead to overvoltages on one pole, on the healthy pole, in case of during the restoration. And therefore, within the project, we assessed how to use, for example, DC choppers, AC side zero sequence grounding, such as, for example, zigzag transformers. But we also developed a converter control-based rebalancing method, which just don't need any kind of additional circuitries. And by this, we can ensure that in both symmetrical monopole as well as in bipolar systems, this grid voltage restoration can happen relatively fastly, and that there are no significant overvoltages during the grid restoration. And after the grid voltage restoration, For sure, also the active power has to be restored, but this can happen relatively quickly within this strategy because there's no need for any current limiting line inductors, because we do not need to limit the current in the beginning, because the breakers do not interrupt during high currents, but just during the low current phase. So more in this direction. So overall, there are no current limiting line inductors in the system, and this makes the restoration, the active power restoration, relatively fast. How does it look now in terms of performance? So on the one hand, you can see this, you can see an exemplary case in our 4-terminal monopolar grid, which you just have seen before. So this is a low impedance pole to ground fault, and the voltage on the blue pole, so the positive pole, collapses, while the voltage on the healthy, the gray pole, stays more or less around its nominal value. After some tens of milliseconds, the fault can be separated, and afterwards the grid voltage restoration takes place. And as you can see here, there would be this kind of overvoltage, and here we overcome this overvoltage by using a DC chopper. And as just introduced, there are several solutions for this, but here it's a DC chopper. And overall, the grid voltage can be restored to its nominal values within, in this case, around 70 milliseconds after the fault occurs. And the active power restoration, you can see here, so that takes place also within a plus or minus 10% band around the nominal values. Within maybe here it's 90 milliseconds, and worst case maybe 120 milliseconds. But the nice part about the strategy is that also the reactive power is not disturbed during the, or not significantly disturbed during the process, because the converters can be continuously controlled. And on the right side, you can see an overview about a broad range of fault cases. So high impedance, low impedance faults over like more or less everywhere in the grid. And you can see that the fault separation time varies here between 20 and 50 milliseconds. The active power restoration time is 70 to 150 milliseconds. And the transient energy imbalance for the grid, so per point of connections, is around 20 to 70 megajoules, depending on the fault case. And overall, we can conclude here that the full bridge-based protection strategy can be a competitive alternative to DC circuit breaker-based strategies for relatively small grids. And what Patrick, so my colleague, has published a nice paper about this, that it also can be extended to larger grids using a partially selective approach. So overall, I would like to conclude here, or to close here with the session, and you will see the demonstration, especially regarding the coordination of the localization and the detection. This you will see later on during the demonstrations. So thank you very much, and I can hand over to Antoine.
Thank you, Philip. So this is William here. I'm with my colleague Antoine, and we are going to spend the next 40 minutes discussing about how we built up this hardware-in-the-loop demonstrator and what for. So I was involved in promotion Work Package 9 as a technical leader in tasks 9.7 and 9.8 that are related to the demonstration of non-selective fault clearing strategies for meshed HVDC networks. Let's talk first about the system layout used for the demonstration. So we built two HVDC networks for the two kinds of non-selective strategies tested in Work Package 9. There are four main differences between both systems. The first one is the system topology. So real-time simulation models were built from offline simulation models available in previous board packages. Since the simulations were done before using these specific topologies, we decided not to change them and to keep them as base of comparison for our real-time system. The second one is the type of MMC converter. For those not familiar with this, the main difference between them is that half-bridge converters cannot operate during a DC fault that will block, while the full-bridge converter can indeed limit fault currents without blocking its operation. This is at the expense of a larger amount of switches in the full bridge. That being said, for the converter breaker strategy, DC circuit breakers located at converter outputs are needed to interrupt fault currents, while in the full bridge strategy, the converter can actually limit the fault currents. And to isolate the faulty cables, the CBS uses mechanical DC circuit breakers with breaking capabilities up to 20 kiloampere And for the FBS, high-speed switches with residual current breaking capability of tens or 100 ampere are sufficient. So this is the 4-terminal meshed HVDC network in a bipole configuration. First, we find here the 4 AC breakers that connect the DC to the AC side. After the transformer of 1.2 gigavolt ampere, you find the half-bridge MMC converters here. Voltage and currents at the output of the MMC converter are needed. This is mainly to allow the supervision system to understand the state of the converter. And downstream, you find the mechanical DC circuit breaker that protects the converter. The line breakers here, you have one per line end. And these arrows here indicates the communication needed for each one of these elements. So we implemented the IC 6150 communication protocol for this purpose. So for this case, there's a need of a lot of communication. There's a lot of communication going on between the network and the IEDs, the relays, protection relays, between the relays as well. And we will see later, there is also a supervision system. So we implemented a supervision IEDs as well. So a lot of communication we needed for testing this grid, the strategy for this grid. But to simplify our work, we simulated only one pole. This will require less hardware resources for both simulation and communication. So another view of this network is the communication architecture. So here we see only the relays of all this network for terminal network. So IEDs stand for intelligent electronic devices, which actually relays and every controller you find in the substation now are intelligent electronic devices. So we're calling them now IEDs from now on. So here you see in red arrows what we call a goose message, which is the carrying information about the state or tripping signals between the network elements and the IEDs, and sample values, which are measurement values like currents, voltages, coming from the emerging units, which are units that transform analog measures into digital packets of informations, which in our case is following IEC 6150 communication protocol. So there are 4 layers of communication for this benchmark network. The first line of communication is between the network devices and the protection relays to send measurements, breaker states, as I said before. Between relays for line breaker modules, for example, because they have to exchange fault current direction between them in order to identify the faulty line. Between relays and station supervisors to communicate the state, like for example, of the AC breakers or the state of the MMC converters, and also to be able to control these devices. And also between station supervisors and relays in order to be able to get the state of the DC breakers and send also opening and closing orders to these breakers. Central supervisor communicate also with the station supervisor. So there is a central supervisor that is the only IED that receives information from the 4 stations, which normally are geographically distant. So in summary, a total of 11 sample values and 99 goose messages were needed to perform startup and protection operations. Now, this is the 4-terminal grid that we use for testing the full bridge converter-based protection strategy. The system is an asymmetric monopole. We used full bridge converters that can limit fault currents to 0, so there is no need for converter breakers in this case. Line breaker modules here present the residual current breaker in series with a high-speed switch. And the system can start from the MMC control model. So no supervision controllers were implemented, and supervision is not needed during the protection sequence either. Now, the communication architecture for this test case is simpler than the CBS strategy, since we don't implement here IEDs for supervision. So here we have only 2 layers of communication. The first one between the network and the relays of line breaker modules. The second one is between the protection relays, and which is actually used also for the identification algorithm, which is the same as the CBS. We're going to exchange the direction of the current between the line ends to identify the fault location. So here a total of 8 sample values and 43 goose messages were needed for the protection. Now, before going forward, I wanted to explain how we achieved how we managed to get to put in place this hardware in the loop demonstrator. So the first step in our demonstration workflow was to put in together different models such as MMC converters, DC breakers, cables, and all the power and control connections. This will become our meshed HVDC network here that we simulate in HYPERSIM, which is the software we use for real-time simulation. But since this is a very complex system, we need first to test it in an open loop. We usually do this first. We predefine different operation modes by using fixed timings and some rules. Our main objective here is just to test that our models can follow a specific sequence of operation, they interact well, and the results are consistent with the expected behavior that we obtain from offline simulations. Then, once we validated the behavior of this network, we want to automatize the system at the intelligence provided by the supervision and protection algorithms. In this step, also known as software in the loop simulation, we test that the algorithms are well integrated to the simulation and that the network is still working and as expected under the control of these algorithms. A sub-step of this can be also to implement a loopback communication. So we send out all the messages, all the outputs from the system, and loop them back to the supervisor and protection that are also in simulation. Finally, we reach the hardware in the loop tests, where the supervision and protection algorithms are embedded on their respective hardwares, so they become what we call IEDs. They are interfaced to simulation that's still running in HYPERSIM using a input-output interface that in our case is IC61850. Now I will hand over to Antoine. We'll explain you the next part of the presentation.
Okay. Thank you, William. Hello, everyone. My name is Antoine Gislac. I am a research engineer at SuperGrid Institute. I worked as part of WORKSPACE on the implementation of the hardware in the loop demonstration for both protection strategies in DC Meshed Grid. Okay, to begin with, I am going to present all the elements, both hardware and software, we implemented in order to run the hardware in the loop test. We will divide this section into an hardware and a software part, and begin with the hardware sections. So first of all, let's talk about the user's workspace. On one hand, a performant user's workspace is needed to run all the software required, but also to ensure an easy and reliable remote access to our external hardwares. On the other hand, several monitors are needed to facilitate the testing and monitoring process. So this workspace is our graphical user interface in which we will manipulate most of our settings. Now let's talk about the real-time simulator. The grid will be simulated in real time in a OP5700 target from Opal RT. Its hardware properties are described in the table. It contains 2 Intel Xeon CPU, each with 8 cores, and 32 GB of RAM. The Opal target analyzer called HyperView enables us to monitor the target loading during a simulation. The principal data to look at is the stretch step. A stretch step occurs if a simulation step is achieved in a longer time than the time step given. In that case, we are not in real time anymore, and this step is not considered. So, our workstation and the target communicate via the TCP/IP protocol through an Ethernet cable. It is a bidirectional communication. We can compile the model into the simulation and drive it in real time from the workspace, and receive simulation results from the target via scopes. So now let's talk about the intelligent electronic devices. In SuperGrid Institute, we decided to prototype our IEDs on Raspberry Pi 4B. You can see in the hardware characteristic that they are basically microcomputers. The biggest advantages of this latest version of Raspberry Pi is the native gigabit Ethernet port, which is essential for reliable performance with IEC 61850, which use the Ethernet protocol. So RPI run on a Linux-based operating system called Debian, in which you can have all the development tools required. 20 Raspberry Pi have been mounted on a rack. For the converter breaker protection strategy, we used 11 IEDs for the protection and 5 IEDs for the supervisions. For the full bridge protection strategies, we use 8 IEDs only for the protection, as the supervision was included in the simulation. The target and the IEDs will communicate via IEC 61850 in a local area network. Therefore, sample values and goose messages will flow through a bunch of Ethernet cable linked all together thanks to an Ethernet switch. So that's all for the hardware part. We will now tackle the software part of the hardware in the loop setup. The main software is of course the simulation software, which is called HYPERSIM. It enabled us to build and compile the model, configure the target's IEC 61850 communication, and drive the simulation in real time. It is linked with the scope view software, which displays results called from the target. We can create with these softwares the 4 terminals Meshed DC networks required for both strategies. Then a software to have a remote access to the Raspberry Pis is required. It is called Mobile Extern and offers access to the Raspberry Pi's hard disk and its Linux terminal. We can then modify code and launch algorithm without plug-in or unplugging hardware. So now both IEDs and the target needs tools to use IEC 61850. A built-in driver is implemented in the target. However, we still need to feed it files called IED capability description files, ICD files, that we make with the ICD designer softwares. It is less trivial for the IEDs. The communication has been crafted via an open source C library called libiec 61850. Finally, to monitor all the Ethernet traffic, we use a packet tracer called Wireshark, which gives a lot of information about capture packet. So we saw the hardware and software parts of the HEL setup. I will make a sum up of the big steps achieved to make this demo. So finally, we had to build the HYPERSIM models, make a collaboration with RWTH lab for the models and algorithm, implement and validate the real-time models, implement the devices under test of our HEL setup, and make the code. So make the code of the IED, so the algorithm, and make the code for the communication. We will go through these steps before presenting the result of the demonstration. I will now hand over back to my colleague William Leon Garcia for the presentation of the HYPERSIM model. Thank you.
Thank you, Antoine. Now I will discuss about the real-time models used in this demonstration. First, this is a view of the HVDC network built in HYPERSIM. The system was described earlier. In this slide, I would like to only make emphasis on the effort we made to build this system from specifications provided in other work packages. The most complex models are MMCs, DC breakers, and cables. But at the same time, there are lots of documentation in promotion, and also we have experts at SuperGrid Institute that helped us building up those models from scratch. We ended up using around 1,000 network elements and 2,000 control blocks from the HYPERSIM library. And this is how the HVDC network for FBS looks like. This model was given by RWTH, completely functional in offline simulation and with a nice documentation. Of course, in order to use it, we had to understand how it behaves as well. The first task at SuperGrid was to be able to run this model in real time. And this is done in HYPERSIM using tools to split the system into tasks and processes. So these tasks are later shared among a set of available processors. Up to 10 processors will run in parallel to solve such a system. We needed some time to further split tasks, and this is done adding the coupling elements at specific locations. So at the end, up to 1,200 network elements and 1,800 control blocks from the library we needed to build up this system. For both MMC topologies, half bridge and full bridge, we used a semi-analytical average model. This model can represent the behavior of the MMC converter under normal and faulty conditions, so we can perform fault studies to validate our protection sequences. Supported by SuperGrid and RWTH researchers, we were able to implement both. So we were able to implement the physical and the control models. So in HYPERSIM, and due to the complexity of such technology, we had to spend several months actually trying to find a stable version for our MMC models. Now, the circuit breaker models used were the following. So for the converter breaker strategy, an active resonant mechanical DC breaker was built from Work Package 6 documents. This was a choice made because we knew the model from contributions that SuperGrid made to Work Package 4. So reproduce this model in real time was not difficult, and it allowed us to better represent the opening and closing operations of this breaker for a converter breaker strategy, which is a very, very important operation for this strategy. For the reclosing, the converter breaker uses also pre-inserted resistors, as Pascal explained before. The model is controlled by the protection ID, and it also has some internal logics to coordinate the different switches inside the breaker and respect the operating times of the different switches. And for full bridge strategy, we used ideal switches with adapted thresholds, such as a breaking capability, the voltage threshold, and opening delays to respect the main high-speed switch specifications. These are two reasons. There are two reasons actually for this. One is that validating the operation of the high-speed switch, it is out of the scope here. And the second one is that we only need to open the switch on the faulted cable once only, and never close it back. So model could be simplified. So this is the curves that superpose the breaker models in offline and real time, just to see everything was fine. Now DC cables that we used are wideband cable models, which is a cable able to represent different transmission modes at different frequencies. It is an accurate model that will give us a nice representation of DC fault transients. Some assumptions with respect to the cable has been made in order to simplify the model and avoid reaching the computation limits of our simulation target. So one is that the screen was only grounded at the ends of the cable, so we avoid having a high amount of cable sections. So we only had 4 cable sections in order to have 4 fault locations, but the grounding is only at the ends. And also we neglect the effect of the screen, so we can choose a model that represents only the core of the cable. So we have 2 conductors instead of 4. Another important model that we developed at SuperGrid especially for converter breaker strategy was the supervisor. So the supervisor allows to observe the state of the system and take decisions in order to start the system or restore it after a fault has occurred. So the associated system can be, in our case, it is the entire network. So the grid supervisor observes the whole system using information from station supervisor. So there is one supervisor for the whole grid, and there are 4 supervisors, 1 per station. And for the supervisor, our team provided a state diagram for each supervisor controller and a list of inputs and outputs, so we know how to interface it to the system. And we used the Supremica, which is a software that allows to transform from the design, which is based in state diagrams, to a C code that can be directly imported into our simulations and into our IEDs. So this is how the state diagram for a supervision of a fault, for example, looks like. And now I hand back over to Antoine to explain hardware in the loop setup from here.
Thank you, William. So now we will go back to the hardware in the loop setup, especially the IED prototyping process. So our workflow is composed of 3 main steps for the coding: the specification, the coding, and the communication creation. So first, the specifications are given mainly by the needs of the protection strategy. It defines, for example, the algorithm requirement and its performance. The coding aspect focus on methodology to implement the specified algorithm into the IED, so it will be a code structure. And the communication creation concerns here the learning and use of the IEC 61850 library. We decided to implement the algorithm into C code. Why C code? So the first reason is it's a low-level language which is more suitable to meet high-speed requirements of protection strategies. The second reason is actually more luck. It's that the library, the lib IEC 61850 is the library implemented for C code. So a deeper learning of C has been required to translate algorithm in a structured way. We used, for example, multiple C and H files and structures, and of course, meet the specifications. The advantage is when C coding is well understood, it's way more easy to translate pre-existing algorithm from other languages or from Simulink, MATLAB, etc. So let's go now more into details for the structure of the code. We used an object-oriented approach via the C structure data type. So to explain this, relays are structures. We can call it objects, call them objects containing several attributes as measurement, tripping order, etc. Then the algorithm becomes C code functions, so we could call them methods, modifying the attributes at each execution loop, built either. So the C functions are built either from scratch, so via the specification as the specification from Work Package 4, or from a third-party software which can generate C code. William talked about, for example, Supremica for the supervisors. For the communication aspect, it is managed by different C files that has been built thanks to the library. The advantage of all this process is to have at the end a reusable skeleton for IADs with distinguishable ports. A port which initializes the relays and communication line, an execution loop which runs at a constant time step containing the call of the different methods and the publication of sample value and GUS outputs. First, this has been linked by RWTH lab. Still, a collaboration was needed to understand the algorithm and its specifications. There was a lot of discussion about the inputs, outputs, their links, and aims related to the strategy. The Simulink file was provided, making the translation into C code easier. A tedious part still was to translate time-based Simulink blocks, like delay, for example, into sequential C codes. So, for the supervisor, the C function is created directly via SupraMeca, but as we want this function to act as a method to be implemented in our workflow, we still have to make a link, an interface of the inputs, outputs to the right supervisor attributes. Although we still had to create all the communication processing to integrate it perfectly to our workflow. So now we will talk about an issue which is called the race condition. This kind of issue appears only if you push your simulation to a HIL setup. The example that I will describe happened to us during the implementation. So for the context, the supervisor is now outside the simulation. It is an IAD. Therefore, it runs on its own execution step on an independent timeline. The context, after a fault, the MMC blocked itself. However, as soon as its current is current protection, so the current is low enough for the protection to tell, okay, you can unblock, the blocked state signal comes to 0. Therefore, you have a pulse of a certain time. On the side of the supervisor, to pass through the next step, the supervisor checked that state signal. That means it checked if the MMC is blocked. The main point is, as the supervisor is a state-based machine and not a time-based machine, we can't know when the check will happen. First case, the supervisor checks when the blocked signal is at 1. The state transition condition is met, and the supervision state machines continue the process. A second case could be the supervisor checks too late, that is to say when the signal is 0. The state machine is therefore stuck to its old state and can't continue the process. That's a race condition. This little joke looks like our case. The answer is given before the checking and blocks the situation. Quick fix for race condition is to make the pulse long enough to ensure that the supervisor will always check at one state. But it's not really robust. How do we choose the time of this pulse? What if there is an unexpected delay? Another most robust way would be a kind of acknowledgement system where the state machine would interact with the MMC to confirm it received the good information. So basically, these are all just suggestions, but the main point is that it raises the question of how to treat this kind of race condition. For that, some investigation in the literature and our know-how is required. We will now attack the last step of the HIL demonstration, the application and integration of the IEC 61850 communication standard in a HIL setup. First of all, let's make a quick presentation of the norm. it is a norm to transfer data between intelligence devices. It was created with the upcoming of digitalized automatic substations. It was made to be interoperable and for quick transmission, which made it suitable for protection. The interoperability aspect is very important in the context of European NTDC networks, including a lot of different constructors. Its rapidity is obtained thanks to two main points. The possibility to use optical fiber as the transport layer and the direct use of the Ethernet protocol for sample values and GOOS, which is the lowest logical layer of the OSI model, therefore minimizing packaging and unpackaging time. So IEC61 has its own semantics that we need to understand. It uses an object-oriented approach. We can see that on the layer-based schema render. You have the physical device layer, the logical device layer, the logical nodes layer, and the data object layer. Two messages of IEC 61850 takes care of the real-time transmission parts. You have first the sample value to transmit digitalized values, and the generic object-oriented substations event called GOOS to transmit logical event. So the main challenge was to make HYPERSIM and Raspberry Pi communicate with this standard. It is possible. These are different devices, but they could communicate each other with the same norm. On the HYPERSIM side, we used our understanding of the norm to fill IAD capability description file in order to fit the IEC 61850 driver of the target. On the Raspberry Pi side, we use the open source library. At the end, both devices was able to communicate. The IEC communication was interoperable as answered by the norm. You can see here that a lot of communication was made. Here are just some numbers. A good communication architecture is therefore important with so much communication. Different aspects have to be taken into account when building the architectures. Here we have the communication of only a part of the converter breaker strategy. As we see, we have already a lot of signal just for one station. Hence, a good naming convention is mandatory to avoid confusion. Also, we need a clear and unique definition of the communication link. By that I mean who is talking to who. Finally, we need to identify this communication link by an identification process. We use the logical path defined by the norm, and as IEC is an Ethernet protocol, we also use MAC addresses. Last but not least, in order to test the communication, we use the Wireshark packet tracer software. It can capture the packet flowing through the networks. Here's an example captured during our tests in which we can identify different parameters. The type of messages, here we can see it's a GOOS packet, the identification parameter, the MAC address and the MAC address and the HAP ID, the name and therefore the link. Here we see it's a message going from the station supervisor 1 to the MMC 1. And of course the content of the message. Here we can see the GOOS transport 6 integer and you can see their contents here. So thank you very much for your attention. I will now hand over to William for the demonstration of the protection strategy and the result. Thank you.
Thank you, Anton. So I propose we take a 5 minutes break, and then you can come back at let's say 11:25, let's say, so we can continue with this part of the presentation. Thank you very much. Enjoy your break. Welcome back. It's William here. I hope you enjoyed your break. Now we can go on with the presentation. I'm going to continue with the results of the HIL demonstration for some specific cases. So the first one will be about the converter breaker protection strategy. But first, we're going to check the startup procedure for the grid, the network that we used for testing this strategy. The first case scenario So it's the startup. This is important because we can appreciate here the operation of supervision IEDs. So in the next slides, you're going to observe 5 graphs all the time. So you have up here the voltage of each bus bar. You have also line converter or line currents. Here we're going to check at only converter currents. The power, active and reactive power of the four stations, the states of the 4 MMCs, and the state of all the breakers. So just for the startup, we're gonna also see the AC breakers, but for the rest of the slides, you're gonna check only the DC breakers. I will first show you how we see the results when you run the simulation, and then in another slide we will go step by step. When you run simulation, you can see how the system is energized here. So I'm gonna go run it. So now on the left side hand, you can see the goose messages captured by Wireshark. So according to the color code that I proposed to you here, so you have during the startup a lot of contribution from the central supervisor. So there's a lot of communication between the stations and the central supervisor. Now we go step by step to analyze the startup procedure. You see that here you see all the DC breakers closed now. And they become green in this graph. So we're gonna also be seeing what happens in this small scheme here. The next step would be the energization of the DC cables. So this is on closing the AC breaker. So you see here the state of the AC breaker, and you can see that the voltage of the DC bus is starting to rise up. So we will reach around 70% first. So there is an AC breaker, but there is a limiting resistor as well in series to the AC breaker. So the next step would be here to close that bypass that limiting resistor, and you can now reach 70% of the rated voltage. And the next step would be to activate the MMC, one of the MMC converters, and it is put in voltage control mode, so it can rise up the voltage up to the rated value, which is 220 kilovolts. Here you see the activation of the MMC1. And then you'll have the activation of MMC2 that can be seen in here. So this dip here is caused by the activation of this MMC that will drop the voltage because the capacitors, the submodule capacitors of the MMC converter are not charged at the highest level they can. So this is why there is this drop. They will charge the internal capacitors, causing that, but then it goes back to the rated value. Then the same for the third station and for the fourth station. After this, so we see here we activated MMCs, but they are still not connected to their AC networks, respective AC networks. So next step would be to close all of these AC breakers. So this is the order that will be given by the central supervisor. So you see here the states of these breakers. And finally, the power can be now exchanged between the 4 stations. So you see here the ramp up of power and the different steady state values of current and power. Here you can see also there is since the beginning there is some reactive power that it is being exchanged between station 1 and the AC network. So this was the startup procedure. Let's go forward and look at the one first fault case scenario, which is in this case a pole to ground fault in cable 2.4, in the middle of this cable actually. So when you launch the simulation, again, here you're gonna see as fast as we observe it when we do the simulations in the lab. So you're gonna see on the right side hand all the goose messages. So since the fault is in cable 2.4, you usually should see a lot of blue and green in this right tab if you follow the color convention. But also at the end, you will see a lot of yellow and the other colors because there is a restoration going on, and the central supervisor and the station supervisors will take a role in that. So in the next slide, let's go step by step in this fault scenario. So the first thing that will happen after fault inception will be that all of the MMCs will block. So you see here the fault currents rising really fast in the lines. So this is current measure at the lines. So after the bus bar on every feeder of cable departure, and you see all the voltage of the DC bus bars dropping near zero. So here the state shows also that all MMCs are blocked. And the following step would be to interrupt the fault current. This is done by opening the converter breaker modules, all of them. So here you see all of them opening and the current dropping back to zero. Next step would be that supervisors will know that all converter breakers are open, so it can activate back MMC 1 and 2, which are connected to actually AC transmission networks, not the wind farm. So here they can provide AC reactive power to the AC network. So they are activated back, and here you can see the light blue and black lines, the amount of reactive power they are injecting to the AC network. Next step would be to isolate the faulty line. This is actually happening while in the meantime, because IEDs from these lines are able to identify the faulty line very fast. So here you can see that around 25 milliseconds after the fault inception, that is at 4 seconds, you can see both breakers, line breaker modules 2.4 and 4.2 are open and isolate effectively the faulty line. So here we have no longer currents, no voltage in the grid. So the next step would be to recover this voltage. This is thanks to the reclosure of converter breaker modules. So this 1, 2, 3, and 4 here. So you can see there is a limitation of the current spike here. That is thanks to the pre-inserted resistors that are inside the breakers. And the voltage recovered here up to around 300 kilovolt. I have to recall that station 1 and 2, these two MMCs are already activated, so the voltage can come back to the rated value. And after that, stations 3 and 4, so the supervisor will tell them everything, will tell them that the voltage is back to the rated level, and they can come in and exchange the power again with stations 1 and 2. And since the fault was in cable 2.4, so you can see here we removed the cable 2.4, but we can still have a path between a connection between the 4 stations. So the power flow will be the same as the pre-fault power flow values, but you can see that one line current is 0 here. So at the end, yeah, this is the steady state values, just to check here better that those are the same values. Now let's check another fault case scenario. In this case, we're gonna look at the backup sequence in case of pole to ground fault in another cable, which is 1.3, but in this case, converter breaker 1 will fail to open. So here again, let's see how this how we'll see it in the lab. So on the right hand side, you're gonna see the goose messages, and you're gonna see a lot of red and black at the beginning, and then a lot of yellow as well. So indicates that the network is working well. So let's go step by step for this case. We have first in steady state, and if we apply a fault in the middle of cable 1.3, again the 4 MMC stations will turn into blocking state to protect themselves from these high fault currents. And the next step would be the fault current interruption. So in this case, converter breaker 1, we assume it didn't open. But one of the advantages of this strategy is that actually having converter breaker and line breakers that have enough breaking capability, they actually have a breaking capability of 20 kiloamperes. So the fact of having that is already a backup protection. So line breakers, actually, in the case of the failure of one of the converter breakers, line breakers still have the capability to interrupt the fault currents. So that's why we see here breaker 1.3, it's able to open after some time. It is a bit longer because the converter breakers, they just need to know there is a fault. They don't care where the fault is. And the line breaker, we have to wait until the line is identified. The faulty line is identified. So once after this, the next step would be, again, STATCOM mode. So for the station 2, everything goes on well. So the supervisor knows that this converter breaker is open. It starts already the STATCOM mode. So you can see here, the light blue line, the amount of reactive power being sent by station 2. And the faulty line isolation already happened before, but just here in animation, and just remove the line concerned by the faults. And you can see that since substation 3 was the antenna was connected through only one line, we lost the station for the next steps. So the station will be removed, and we can only now operate with the station 1, 2, and 4. And since this is isolated, for the station 1, everything's okay. So the MMC1 can be activated back and put in the STATCOM mode as well. So you can see the light and black line here showing the reactive power. And here the MMC states activating back again. So after that, we can recover the voltage back to its rated value. This is done by, again, central supervisor that sends the grid and tells station 2 to put back the voltage or rated level remain. We have to say here that since this converter breaker is not working, the supervision will tell it not to close back again, because we cannot ensure a reliable protection with it. So this station is also isolated. So we actually are going to work only in a point-to-point configuration using substation 2 and substation 4 for this backup scenario. So once the voltage is restored by station 2, station 4 can be unblocked again, and the power can be exchanged between station 2 and station 4. And that's what we're going to see in the rest of the simulation. So here you see that the line 3 disappeared from the power flow, and we still have 3 lines, but only 2 power exchange between 2 and 4. That was it for the converter breaker protection strategy. Let's move on to the full bridge converter based protection strategy. I'm going to show first a fault, a case scenario of a pole to ground fault in cable 1.3. So here again, you're going to see a lot of black and red goose messages that corresponds to the stations in which the stations where 1.3, IED 1.3 and IED 3.1 are located. So this is how we see it in the lab. Yeah, you see so gray and red mainly. Now we go step by step to explain this strategy. First, when you have a fault inception, there is a detection of the fault at the full bridge MMC converter, and they will turn into, it's not a blocking mode, but it's a different control mode in which they try to reduce the fault current. So you can see here how the fault current limitation is done by these 4 MMC converters. So they will put DC voltage at negative value actually during the fault, so they can annulate the effect of the fault. Next step would be pole rebalancing. You can see here that the healthy pole almost doubles its voltage. So it was minus 320. It goes up to 450 negative value, and this is done thanks to a change of control mode of stations 1 and 3, which are the stations that are aware of the fault, because the fault is in the line, the cable 1-3. So IEDs communicate that there is a fault to the converter, and the converter changes its mode in order to perform pole rebalancing, and that you can see here the voltage value going back to 0. After pole rebalancing, or during the pole rebalancing, there is a isolation of the faulty line. So here there is a control mode that is changed also in the converter, in order to limit the faulty line current to 0. So it's a dedicated control mode in order to bring back this current to 0, because high-speed switches here, they only have a breaking capability up to 100 ampere. And the isolation is also only possible below 5 ampere, I think. And once this is done, so current is the line 1-3 is isolated. In this case, again, since we had a fault in cable 1-3, we lose one station here, station 3. It doesn't have any other connection to the other stations. So now voltage has to be first restored, and this will be done by station 1. And after that, the other stations will also change their control mode in order to exchange power with station 1, so station 2 and 4. So you can see, if we see the steady state, you can see that after the post-fault steady state values are different than the pre-fault values. So there is an exchange between, there's a lot of power injected by station 4, but mainly almost all of the power is going out from station 2 and station 1. Now there is some arrangements here that has to be done after with if we include supervision, for example. And now a specific case for this full bridge converter protection strategy is a pole-to-pole fault. Since we implemented, since the topology of this network is a symmetric monopole, there is a difference between a pole-to-pole and a pole-to-ground fault. So it is interesting to study a pole-to-pole here. So we're gonna put a fault in cable 2-4, in the middle of cable 2-4. Let's see what happens here. You're gonna see a lot of goose messages in blue and green, which corresponds to stations close to the fault. So effectively, you can see here green and blue goose messages. And let's analyze this step by step. So if we look at this, first is the detection of the fault by MMC converters, followed by a fault current limitation, as in the pole-to-ground fault. This doesn't change. So here we see how voltages are forced to be negative again. Oh, sorry. Now here, all the voltages of both faulty and healthy pole goes to 0. And we have higher fault currents, but again, thanks to the converter, we can bring them back to 0 in order to, in the next step, open the high-speed switches here. So we remove the faulty line, which is 2-4. After this, we have the voltage restoring. So we change the mode of converters to 1 and 3 in order to recover, 2 and 4, to recover the voltage back to their rated values, while station 1 and 3 are still only controlling current to 0. And after that, all the converters will turn back to normal control mode and exchange power between the 4 of them, because this is the same case as the first one I showed for the converter breaker strategy. So we have the possibility of exchanging power between the 4 stations. So here you have at the end the same post-fault power values as the pre-fault values. So that was it for this demonstration. Thank you very much for your attention. Now I will hand over to Laurent Chedeau to give a summary and conclusions.
Okay. Thank you, William, and thank you, Antoine, for these very interesting results. It's now time to conclude. In summary, the main objectives of Work Package 9 were assessed for both converter breaker strategy and full bridge converter base strategy. HIL tests were performed using real-time models developed in HYPERSIM to build up 2 4-terminal HVDC networks. AEDs for protection and supervision were tested, and we could perform primary and backup sequences for different fault test scenarios. Use of IEC 61850 as communication protocol for this test showed that 2 different pieces of hardware were able to exchange comprehensive data for the application of protection and supervision. Supervised control and protection was successfully designed, implemented, and tested, including startup and restoration. Okay. Next step, work is never finished. We did the demonstration of protection strategies. We want now to perform full validation of these strategies, evaluate key performance indicators defined in promotion, test the robustness of the supervisor in case of strong failure, typically voltage and power restoration with a station failure. We have a real-time simulation. We want to obtain real-time test bench. For that, we have to upgrade relays, supervisor, network, and communication architecture with more control and protection function developed in SuperGrid Institute. Thank you very much for your attention. The complete demonstration will be available in Promotion's official YouTube channel. A link is available from the Promotion website. We now go to the question. I will require a few seconds because I have to share my screen. Okay, so we have a few questions. I try to group some questions together. The first one is for Philippe, is about the full bridge MMC. And the question is, how do you define the high impedance fault on HVDC side?
Okay, thank you very much for the question. I'm not sure what is meant by define the high impedance fault. Maybe I can give some insights on how to treat low impedance, high impedance faults and where the differences are for the full bridge protection strategy. So first of all, a high impedance fault is for us a fault in the order of 20 ohms. Just it's an exemplaric value just to stress or to analyze the stress of a high impedance fault on the protection strategy itself. So in a cable-based system, usually since everything is, and especially for offshore cable-based system, all cables are grounded and the return path is usually quite good. So we are more in the below ohm range for fault. But in case there is a high impedance fault, the overall discharge process into that or through that fault takes longer because it's just more resistance in the fault current path, and so the converters have to work more to actively discharge the DC network. And like especially during high impedance faults, you can really see the difference between active discharge of the grid and just like a passive discharge, for example, if you block the fault blocking converters. So here our analysis showed that it's really beneficial to have an active fault current control also to treat high impedance faults. But overall, these can be treated and overcome with a protection strategy. I hope that kind of answers the question. And if that was not exactly what you meant by the question, please just write me an email after the session and I will come back to you. Thanks.
Thank you, Philippe. Other questions are more on the demonstration setup. The first one about the GUS communication.
Okay.
So GUS communication.
Yes, actually both. So binary data is no, sorry. GUS communication is only for binary data. Analog is used for that is we use the sample values. So it's not it's measured values. Actually, it's not actually analog signal. It's a digital signal because we're still using Ethernet to transmit sample values. But the answer for the question is yeah. For GUS, you can only use it to transmit. No, sorry, I got a confusion. So binary data is just a type of data. So actually with GUS, you can transmit different types of data. I was confused because I was thinking of data that is meant to be states of breakers or states of or tripping signals, but you can actually transmit integers or doubles or floats or any kind of data type. You just need to in the norm, there are different types of data defined for different kind of purposes. But you can always find the type of data that you find in every informatic application. So yeah, the answer is not only binary data. With GUS, you can also use other types of data. And GUS is a protocol that is meant to be used for states or for events, specific events that is not synchronous in time. So sporadic events. So analog data, usually you have a frequency and then you have a period for this data. So GUS, you don't use it for analog data. You use the sample values if you want to send measurements or data that is synchronous in time. I hope that I answered your question. And thank you very much for the question.
Okay, thank you, William. Next one, in the hardware in the loop test setup, how was the model split among the processor in the OpenRT system?
Yeah, so actually it depends on the model we use, but OpenRT by default can split. When you split the model among the processor, there is a communication delay between processor that need to be compensated by the real physics, let's say. Otherwise, you have a false delay in the simulation. So what OpenRT does in the simulator is that if you have a cable which is long enough to have a propagation delay, and that propagation delay is superior to the time step you use, you can split it into two cores, into two tasks, let's say. Sometimes if it's not possible, you need to use a certain element called a decoupling element, which introduce a kind of false physics dynamic to overcome this delay. But it's still a bit, how can I say it, messy to do it because you introduce a false dynamic, so you can really destabilize the system. So I hope it answered the questions.
Thank you, Antoine. The next one is about the real-time step. So what is the signal step time for real-time simulator? And I join another question from another participant. Could you say what the computation time was for the model in the OpenRT system?
So I think signal state time for real-time simulator, you mean about the same, it's more or less the same question. So for the model, we use the 50 microsecond time step. It's fast enough to take into account the protection, how do you say, the events, fault events, dynamics, and the protection. in the calculator, the computation time of the real-time simulator depends on the load of the models, but the main aim is to have a computation time faster than the simulator, than the model time step. Otherwise, you are not in real time. And for that, you split. You can see in Hyperview, so the target analyzer that I presented, the time step, the execution time of each course. So you can, it will depend on the model, but you can therefore split your model into each course and see their real execution time.
Okay, an additional question. Thanks to your answer. You speak about 50 microseconds. Is that true for both benchmark? Or it was a common time step, or do you have a different time step for the two benchmarks?
For the full build strategy, we use the execution time step of Aachen, which is 40 microseconds. I don't. Yeah. We use the time step given by Aachen Lab in offline simulation.
Okay, thank you. The last question deals with the cable modeling. For cable modeling, are you referring to the P section model of the cable? So detail about the cable model used. I think it's more on the demo setup used for the real-time simulation.
No, the cable model is a wideband cable model. So you need, once you know all your geometry of the cable and the characteristics of the different materials of the cable, you can generate a model that is really detailed and accurate, which is a wideband model. So it's not, P section model has constant parameters. The wideband model has different parameters depending on the frequency of operation, and it can represent the different modes of operation of the cable. So it's much more complex than the P section.
Okay, so that's all for the question. Okay, one more time, thank you very much for your attention. As Philippe explained before, if you have other questions coming after the presentation, you have all our coordinates in the presentation available in promotion website. So don't hesitate to contact us by mail, and we will try to answer and to exchange with you for all detail about this presentation. Thank you. This is the end of the presentation. Bye.